Today we want to continue talking about integration by parts, which is our anti-product rule. If you put the integral, the secondary integral, on the other side with the integral of u dv, you can start to see the product rule. So think of taking the derivative of uv. That'd be the derivative, that'd be u prime times v plus u times v prime. So if we go back the other way, if we integrate the dv, that'll be v, and this will be the integral, and this will be just u. So there's a dv and a regular u, there's a du and a regular v. So that's where we could see that the product rule parts, the product rule structure shows up in parts. So integration by parts is our anti-product rule. We don't have an anti-quotient rule because we've got substitution in parts, and we never really needed the quotient rule to begin with. Let's take a look at some things that we get from integration by parts. If you would recall, one of the integrals that we did last time was the integral of, I can't remember, I think it was 5, x to the 5th natural log of x dx. And if you recall, the integral here was 1/6 x to the 6th times the natural log of x minus 1/36 x to the 6th plus c. If you recall, we started off following the same plan that we did on the first two parts problems that we've done, because we've done a total of 3 integration by parts problems. We should be experts by now. I don't know what y'all are complaining about. If you recall, the first time we tried it, we put u as x to the 5th and dv as natural log of x, and that stopped us from that one because we did not know the antiderivative of natural log of x. So recall that we tried u equals x to the 5th and dv is natural log of x dx. We couldn't use these parts because we didn't know the antiderivative of natural log of x. At the time, we had to go back and try something else because we did not know the antiderivative of natural log of x. So here's one of the fun things that we can do with integration by parts. This is especially effective when we have a function whose derivative changes form. We go from some transcendental function like the natural log of x to an algebraic function like 1 over x when we differentiate. So we integrated x to the 5th natural log of x by just switching the order, and it was a pretty simple integral. Let's take a look at this integral. In this integral, all we have for parts is natural log. So all we have for parts is natural log. We know we can't put natural log in the dv section because we don't know the antiderivative of natural log. And if we did know the antiderivative of natural log, then we wouldn't be doing parts. We would just be writing down what the antiderivative of natural log is. But we're pretending that we don't know. So to set up parts, we're going to do like we did yesterday. U is natural log of x. And that leaves for dv just dx. We think of it as 1 dx. we can do integration by parts with everything in the derivative section, except for the dx. Once again, we have to deploy this way. I can't put natural log of x over here with the dv because that's what we're trying to find out. If we knew that, we wouldn't be doing this process. We would just be writing the answer. So, step 0, this is not a substitution problem. Step 1, choose your parts. Don't have any choice. U is natural log of x. dv is just the dx. Step 2, find the other two parts. So if u is natural log of x, then du is 1 over x dx. And if dv is 1 dx, then v is just x. Differentiate to find du, integrate to find v. Step 3, put the 4 parts into the parts formula. So I'll have uv minus the integral of v times du. And here, when we multiply v times du, x times 1 over x cancels out, and we're just left with dx. Because we have 1 over x multiplied by x, and that's just equal to 1. Now we can integrate the 1, that's our secondary integral. And we find out the integral of natural log of x is x ln x minus x plus c. Now, at this point in our calculus careers, if we wanted to go back to that x to the 5th natural log of x and integrate it the other way, we absolutely can. Because at this point, we now know that the integral of natural log of x is x ln x minus x. And now that I've said it twice, everybody remember that exactly forever. Because that's how math classes are supposed to work. I just need to say things one time and show you how to do a problem one time, and then you know it forever, right? That's just how the human mind works, isn't it? No? Oh, darn. Oh, well, I'm sure it's not what we'll base an education system on for a very long time. I'm sure we'll find something better. And we've only been doing this for, I don't know, as long as we've been doing school. Dang it. You'd think if we were so learned, we'd come up with a new idea. What are we talking about? Oh, yes. So at this point, we can go back and we can put the dv in the put natural log in the dv slot. But remember, the goal is to try to take our integral u dv and our secondary integral, create a secondary integral v du that is simpler than what we started with. So this gets a little bit messy if we switch them around, but we can do this now. At this point, though, you might look, if we have some x to a power ln x, we had x to the 5th ln x, we had 1/6 x to the 6th natural log minus 1/36 x to the 6th. And the same thing happened down here, only instead of a 5 going into a 6, we had 1 or 0 going into a 1. So we had x to the 0. So if I said that x to the 7th natural log of x, we could probably guess what the pattern is going to be, because the same thing will happen. one of the natural log gets differentiated to a 1 over x. Our integral here goes up 1 power and then goes down 1 power. And so if we had to integrate x to the 7th natural log of x, we'd have 1/8 x to the 8th natural log of x minus 1/64 x to the 8th. It's a very predictable pattern. Let's take a look at this problem. X to the 5th natural log of x dx, and deploy things the wrong way now that we have new information. When we first started this parts process, we did not know the integral of natural log of x, but now we do. And so we should become curious, like, well, hey, now that we know that the integral of natural log of x is, or what the integral of natural log of x is, should we try this problem again? And some of you will be like, practical. No, that's crazy. We already have a method that works. In fact, we already know what the answer is. We don't even need a method anymore. That's because y'all are engineers. Engineers just want to build something, make sure it works, and then not worry about it after that. Well, get paid and then not worry about it after that. But we're trying to pretend that we're not just here for certification and approval. We're here to learn things, and so we have to explore our curiosity. So this case, du is going to be 5x to the 4th, and that's where the dx will show up again. And now that we know the antiderivative of natural log of x, we can write v is x ln x minus x. Now, step 2, find du and v. Step 3, put together into the parts formula. So that's going to give me an x to the 5th times x ln x minus x. That's uv. Then we have to do minus the integral of v times du. And now it's going to be like Hudson and Aliens. Sir, is this going to be a calculus problem or is this just another algebra problem? Then I'm like, oh, we're going to use the distributive property, and then you're like, oh, it's just an algebra problem. Now we can start seeing where all these parts are going to come from. Here I'm going to have that x to the 6th ln x minus x to the 6th. And that's certainly part of the form that we had above. But in this case, we're going to have 1 whole x to the 6th ln x. And we're going to have to get cut down by a fraction. We're going to have to lose 5/6. We're going to have to be subtracting 5/6 x to the 6th ln x. I wonder where that's going to come from. Notice that here's an x to the 5th, that when we integrate it is going to become an x to the 6th. Here's a 5, and we're going to be dividing by a 6. So there's going to be 1 x to the 6th ln x minus 5/6 x to the 6th ln x. And that's where 1/6 x to the 6th ln x is going to come from. So multiply this out. And then let's sort out what our integral should look like. I can factor out a 5. And I'll have an integral. I'm going to multiply this out here as well. X to the 5th ln x minus x to the 5th. Whoa, hang on. I should put parentheses to emphasize that these two are all in the same integral still. Is everybody still with me? Anybody still wondering why we're doing this? If you're wondering, why the heck are we doing this? Don't we already know the answer? The answer isn't the point. The answer is never the point. The process. That's the important thing. And learning things about the process that we're trying to learn to spot. Here's one of them. Notice that we have this secondary integral here. And you should look back at the top of the page and say, dude, shouldn't the secondary integral be simpler than what we started with? And I'm like, well, yeah. And then you're like, oh, well, what about this? X to the 5th natural log of x. That's not simpler than what we started with. And here's the important thing to notice. It's exactly the same as the thing that we started with. I want to recognize when the integral that I started with shows up on the other side of the problem. Because I don't want to have to integrate. I'm already in the midst of integrating this, and I just found 5 copies of the thing that I'm looking for. So I'm going to combine like terms because algebra. And I'm going to gather all the integrals of x to the 5th natural log of x dx onto one side of the equation. So I'm going to look at these 2 terms. Here we're going to have a minus 5 integrals of x to the 5th natural log of x dx. And I'm going to have the distributive property. Minus 5 times minus is plus 5 integrals of x to the 5th dx. Then in orange, we see that minus 5 integral of x to the 5th natural log of x dx. And we go back to the beginning and we notice that that is the integral we started with. So I'm going to add 5 copies of integral of x to the 5th natural log of x dx to both sides. So I'm going to end up with 6 copies of the integral x to the 5th natural log of x dx equals x to the 6th natural log of x minus x to the 6th plus 5 integrals of x to the 5th dx. The thing that we want to notice is that our secondary integral had as a term the original integral that we're trying to find. This is one of the things that can happen when you're doing parts. A copy of the original integral shows up on the right side. Your strategy is to gather like terms. Take the integral, that's the original integral. It's minus 5 copies of the original integral. Just add that to both sides. We have 6 copies. Now I just have to finish the actual easier part of the secondary integral, the x to the 5th, and then divide by 6. I've got 6 integrals of x to the 5th natural log of x. I'm looking for how much is 1. So we'll just divide by 6. Any questions? Is everybody okay? Yes.
So you add to both sides, so it will be plus 5, and y is 6. Is there a
Because there's 1. I started off with one of them over here. I started off with 1. And then I added 5 of them. Any questions? So that's from separating these terms, x to the 5th ln x minus x to the 5th, right? Those are 2 terms. And I just multiplied through by negative 5. So that's why it's negative 5 integral x to the 5th ln x dx. And then the negative 5 got distributed to the minus 5, or minus x to the 5th. So we use the distributive property. So the negative times the negative became positive, and it's 5 integrals of x to the 5th. Any other questions? I can tell there are more. You just don't want to say. So I'm going to leave this. Make sure that after you divide by 6, you end up with 1/6 x to the 6th natural log of x minus 1/36 x to the 6th plus c. Questions? If you want to make sure that this makes sense, here's the way you do it. You pull out a clean sheet of paper, you just start writing what we just wrote, and you explain it to yourself. When you get stuck, you take a look at the other things that I wrote. You try to remember the other things that I said, because right now you're taking notes by just writing down everything that I write down. But your notes shouldn't be just everything that I write down. I'm going to hand you that. Your notes need to be the things that you think are important. So you write down. What did I say that I didn't write down that helped solidify what's going on the page? Question?
So, like simply say steps.
Yes. Step 0, not substitution. That's where I always start. Step 0, not substitution. Step 1, decide on your parts. Choose U and dV. The most important rule here is that dV must be something that you can integrate. Step 2. So step 1 is your given. Step 2, find. So you just want not necessarily steps with descriptions, because that's cumbersome. You want steps with triggers. Step 1 or step 0, not substitution. Step 1, givens. That's your cue for the first line. What are your givens? Just givens. Step 2, find. And then we have to know from the process what that means. That means find du and v. But the step 2 cue is find. Step 3, plug in. That's where you take the 4 parts and put them into the parts formula. So we just call that step 3, plug in. And then step 4, secondary. Then step 5, if necessary, repeat. Because your secondary integral might still be parts. Now, it'd not be a good way to introduce the steps, but it's a good way to remember the steps, because it is succinct. But we have to remember what all those things mean. Step 0, not substitution. Step 1, your givens. Step 2, find. Step 3, plug in. Step 4, your secondary. Step 5, repeat, if necessary. Those are the words that I say to myself once I've committed the parts. Givens, find, plug in, secondary. This problem has shenanigans in it, because you should always be on the lookout for mathematical shenanigans. And it usually comes from algebra. Algebra is where most shenanigans come from. The rest come from trigonometry. And it's all, but if it's trigonometry shenanigans, it's always identities. There's some trig identity. If you get stuck on a problem and they're trig functions, bet you forgot a trig identity. So there were some shenanigans in our secondary. We had in our secondary a copy of our original. And so we were able to add it to both sides. That's your reaction whenever you see a copy of your original show up in your secondary. How's everybody? It only seems like it's a lot to remember, because it's a lot to remember. And you have to remember all of it, all the time, in perfect detail. I'm not asking too much. It's asking way too much. Questions? Comments? Not an example. So as we just pointed out, in some instances, your secondary integral is also a parts integral. So let's write down a generic integral, and we're just going to pretend that it becomes multiple parts. This is one of those things where it's easier to keep things generic, because then you can see the relationships that are going on. It helps to make sure that if you've got an algebraic statement, if you plug in some numbers, that helps you see that it works. But sometimes as we're going through a problem, there's a pattern that we want to highlight. And so instead of leaving or writing 2 times 3 as 6, I want to leave it separated as 2 times 3. So one way we could do that is to try to do a problem, only instead of being specific about what the functions are, just say there's a U1 and a DV1. And we're going to do parts. Okay. So we start with our first set, U1 and DV1. Step 1, givens. Step 2, find. So du is du1 and v is v1. We put together in the parts formula. I think I messed up my labeling. I don't think I need to label things. So we'll have u1 v1 minus the integral of v1 du1. And what we're going to do is we're going to take that secondary integral and say, what if this is a parts problem again? One possible way to deploy our u and v is to just pick up where we left off in our original parts. So one way to deploy the u and the dv is to say u is just going to be the du1 and v is just going to be, or dv is just going to be the v1. Our next iteration of parts can pick up at the last row of our first iteration of parts. So we could set it up where our next u is just where we started, the du1. And our next dv so the previous find becomes the next iteration's given. Just pick up where we left off. So if you use the steps that we named before, the next parts given starts at the first parts find. So instead of stopping at the first derivative of u, just think we're going to differentiate that again. We're going to have a second derivative of u. So we'll end up with u1 v1 minus, and then parts is going to be u2 v2 minus the integral from parts is going to be the u3, oops. So minus, I need parentheses, not an integral. So we end up with these stacked parts formulas. And it's all just going to be u times v minus a u times v minus a u times v minus a u times v. And here is where all of our terms are going to show up. Let's look at an example. What we want to be looking for is uv minus a uv minus a uv minus a uv. That's what we want to envision here. Now we're going to do this with actual functions. Let's suppose we have the integral of x to the third e to the 2x to x. So the first thing we want to recognize about this problem, we should recognize that this is going to be a multiple parts problem. We see that x to the third, that's going to be u e to the 2x will be our integral. Then the derivative is going to be a 3x squared. And our secondary integral is going to be an x squared e to the 2x. And then our third integral is going to be an x e to the 2x. And our last secondary integral, our fourth one, will be just e to the 2x, and that's where parts ends. So it's going to be 3 iterations of parts. Let's do them all at once, because the thing that makes this, that's going to make this go, is we can differentiate x cubed all the way down to 0. So we've identified multiple parts because of this polynomial x cubed. So x cubed is going to be our starting u. Our starting dv will be e to the 2x. The first iteration of parts will say that du is 3x squared. And this is the part where we say, oh, I see where this is going. I'm going to be doing another part where I start with an x squared and it drops down to an x. And so that's when we start the multiple parts protocol. Once we see what's going to be going on, once we notice that we're going to be differentiating x cubed down to 0 eventually, let's just continue to differentiate du down to 0. So once we see this happening, I just take the next derivative and then the next derivative all the way down to 0. So we did 3 additional derivatives. For each derivative, we find an integral. I stopped labeling them at this point. So then I do a 1/4 e to the 2x, then a 1/8 e to the 2x, then a 1/16 e to the 2x. Then we just start stacking UVs. And the UVs all show up down diagonal. Here's a UV. Our first UV will be a 1/2 x to the 3rd e to the 2x. Our next UV is going to come from these two, because that 3x squared and the 1/2 e to the 2x, that's where we're going to start our next parts problem. So the first term is going to be UV. But the second one is behind a negative. So we change the sign. So it's going to be 3/4 x squared e to the 2x. Our next UV will be the 6x and the 1/8 e to the 2x. And our last UV will be 6/16 e to the 2x. Notice I didn't write signs in between. The parts formula has UV minus the integral. So when we stack parts formulas, we're alternating subtracting and adding. Because notice that U2 V2 is behind 1 subtraction, but U3 V3 is behind 2. U4 V4 will be behind 3. We're stacking all these negatives. So once you get through the process and start learning it, you'll say, wait a second, why am I alternating keep the sign, change the sign, keep the sign, change the sign? And it's going to come back to stacked parts formulas. So the idea is the first one, we keep whatever sign it had. So here I say this is a keep the sign. But the next one is, the next UV is behind one negative. So we change the sign. The third term is behind two negatives. So we keep the sign, whatever sign it has. And the last one is behind, let's see, one negative, two negative, three negatives. So this is going to be a change the sign again. We don't want to summarize this by saying alternate the sign. We're having that thought right now because I made a poor choice in going x cubed e to the 2x, because e to the 2x is just always going to be positive when we integrate it. So let's do something with some different signs. Any questions? So when we're alternating, keep the sign, change the sign. We're going to alternate, keep the sign, change the sign. Don't think of alternating signs because we're not always going to alternate the sign. This one happened to alternate. So this is going to be a plus minus, plus minus, plus minus, but the next one will be different. So this one fits the same description as the previous one. We've got x to the third, and then some transcendental function. And we notice that this is the part section. We're probably going to do parts. I like to differentiate polynomials because they differentiate down to 0. And so that's what we're going to try. I'm going to say, let's put u as x cubed. And dv will be sine of 2x. We find du first. That's going to be 3x squared. And then we find v. And this is where we notice that we are going to be doing multiple parts. X cubed drop down to x squared. Our secondary integral is going to be x squared cosine of 2x. So I'm just going to keep going doing parts all the way down to 0. But we got to do this minus 1/2 cosine 2x. So we differentiate down to 0, 6x, 6, and 0. And we integrate for each derivative. Minus 1/2, or 1/4. Sine of 2x. Then positive 1/8 cosine of 2x. And then positive 1/16 sine of 2x. And because I know negatives are so dangerous, I check. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is sine. So I got my signs deployed correctly. Any questions?
So this goes back to the first part, the integral of V1 times it's like going down in part scale into
Yes. Yeah, that integral is just gonna pick up where the, have it take its given from the find of the previous steps. So if I just keep writing UV, 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 UV. Now we're ready to put together it with all the UVs. The first is our original UV. So and this is on the keep the sign level. So I'm gonna keep -1/2 x cubed cosine of 2x. The next term is going to be 3x squared times -1/4 sine of 2x. So the natural sign for this term is negative. Oops, and it should be 3/4. X squared sine of 2x. But this is the second one, it's behind a negative, so it's to change the sign. So I change it to positive. The next one is a keep the sign. That's going to be positive 6/8 x cosine of 2x. Then the next one is to change it, so to go from positive to negative. 6/16 sine of 2x plus c. Normally, I don't care about shortcuts, tips, and tricks, and 8 simple rules to help you crush your next math test. But this one allows us to think about the structure of what's going on and think about repetitive applications of a process. In particular, repetitive applications of a process that has a minus in it. And it's just UV minus the integral of 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 UV. And so this keep the sign, change the sign thing happens because of those stacked minuses from the formulas. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.